Alright, welcome to the second of 3 lectures on linked lists. So in the previous lecture we introduced some of the mechanics of using structures in C, working with pointers to structures so that we can pass the address of a structure, dereferencing using that arrow notation, allocating memory at runtime so we can create dynamically allocated objects as our program is running instead of at compile time. And we looked at some other things like freeing memory, memory leaks, val grind, and so on. And we led up to the idea of a particular type of structure which we called a node, which contained in our example 2 pieces of information, a piece of data, but also a pointer to another node. And we used this structure called a node to create a collection of linked nodes or linked pieces of information that created a list. So we could have one piece of information here, another piece here, and we could connect them together because each node would point to another node. So we made a list containing the numbers 10, 20, and 30. And as long as we know how to find this first node, we can follow its next field to find the second node, and that second node has the reference to the third node, and we could keep going. And so we could build a very long list. So what we want to do in this lecture is 2 things. The first thing is I want to motivate the idea for why we're going to do this, because this is expensive. We've got to do dynamic memory allocation, we've got to keep track of things ourselves, whereas an array will also let us store collections of information, like an array of integers. We could store these numbers. Why would we bother making a dynamic structure at runtime when we could just define an array and store things in there? And that's going to go back to the notion of order of complexity. So that's the first thing I want to do, is motivate this. And then I want to look at the idea of abstract data types and use a linked list as sort of our first deep dive into what an abstract data type is. So those are the 2 things we're going to pursue in this lecture. So let's work with this first idea first, order of complexity. And you know, if you want to store a bunch of data in the memory of the computer, let's say you're reading integers in from some source, maybe somebody's typing them in, you're reading them from a file, and you want to store them in memory, we can use an array for that. So I could, have a series of numbers like 2, 7, 1, 6, 5, 8, 11, and 9. And, I could just put these into an array. So I could start off with a big array, make it, 1,000 elements or something. And, our array has all these different locations where we can store information, and there's an index, integer starting from 0, that we can use to reference each of these cells. And so I could have, some integer length, initialize it to 0, and every time I get a new number, I'm going to store it at the index given by length, and I'm going to increment length. Here's another number, I'm going to store it at index 1, and I'm going to increment length. I get my next number, I'm going to store it at index 2 and increment length, and so on. So we could take these numbers and we can store them in our array. And at the end of this, I believe length would be equal to 8. And then if, we've stored all this data, and then someone comes along and gives us a new piece of data and says, hey, let's store the number 5, same thing. Store it at index 8. So that goes at that location, and increment length. So no matter how long this list is, the amount of work we have to do to store a new number at the end is fixed. So we call this order 1. Order 1 is about the best we can hope for. It means our operation takes the same amount of time no matter how big our data collection is. The only thing better than order 1 would be order 0. That would take no time to execute. Alright, so adding to the end of an array is an order 1 operation. On the other hand, if we wanted to add to the beginning of an array, if we wanted to take a new number and put it right before the 2, really the only thing we can do is move everything down in memory one spot. Copy this to here, copy that to there, copy that to there, and so on, so that that 2 gets moved down to index 1, and then we could store something at the beginning. So add at the start, that's an order n operation. But usually if we're just storing our information in memory, we don't care if it's stored at the beginning or the end of an array, we just want to store it. But there is a case where this is going to make a difference to us, and this is when we want our data to be sorted. So if our array contained the following information, 1, 2, 5, 6, 7, 8, 9, 11, and I shouldn't have tried to insert a 5 because I already had a 5 there, so let's just pretend I was inserting a 4. So suppose I have this information in my array and it's sorted, and now I want to insert a 4. Well, I have to go through my array to figure out where that should go, but if I know that it wants to go right after this 2, I've still got to do this business of moving everything down one spot. And depending on where I'm inserting it, I might have to move, you know, all n pieces of data down one spot so that I can put the new piece of data right there. So add in the middle, that's basically an order n operation. And while we're here, searching for a piece of data, that's order n. If I want to search for an 11, I've got to go all the way through till I get to the end here. If I want to search for 7, or sorry, 3, I have to go all the way through here, get to the end, and say, hey, 3's not in my list. If I want to search for a 1, hey, it's going to be right there in the beginning. I'll be lucky, right? But remember, if so that's order n if our data is unsorted. But if our data is sorted, and we want to look for the number 3, right, I could start at the middle of my array and say, hey, the middle is a 7. I don't have to search this bottom half of the array. I can say, okay, if I have a 3, it's somewhere in the top here. I cut my problem in half. And then I can search a number in the middle like 5. And if that's too big, I'll say, okay, so it's got to be somewhere in here. And maybe I'll search the 2, and that's too small, but there's nothing else in the array. So we can play high-low, right? We've done this in 224. If we have a sorted array, then it takes on the order of log n if our data is sorted. So this is for arrays. So adding at the end, order 1, adding at the beginning, order n, adding in the middle, order n. Searching is order n if it's unsorted, and if it's unsorted, you know, we can just add at the beginning of the array or at the end of the array for order 1. But if we want to search efficiently, we need our array to be sorted, which means when we add in a new piece of data, it's going to have to get added to the middle, and that's going to be order n. So this is not going to be a very efficient way to store information. The orders of complexity are at least n, and sometimes n plus log n. Alright, on the other hand, a linked list we can do a lot better with. So here's our collection of data, and I won't bother breaking it up into the 2 fields. We've just got a 2, a 3, a 1, and a 6. And if I want to add at the beginning, so add at the start, well, that's pretty easy to do. All I've got to do, let's say I want to add a 5, all I've got to do is make a new node and have that point to the beginning. So that's order 1. If I want to add to the end, well, if I have n nodes in my list and I'm starting with the first node, I have to follow the pointers till I get to the last node, and that's an order n operation. And then to add one more thing to the end, that's just order 1. So it's order n to reach the end, order 1 to add. But, you know, we can create a modified linked list that, for example, would always keep something like an end pointer that points to the last node in the list. And now if I want to add, I simply follow that to get immediately to the last node, add my new node, and then change end pointer to point to that. So we can do this in order 1 if we're a little clever. So whereas an array we could add at the end efficiently, adding in the beginning was inefficient, with a linked list we can add to the beginning or the end in order 1. Now adding in the middle, well, to actually insert a node in the middle only takes a fixed amount of operations. Let's say I want to add a 7 between the 3 and the 1. Make a new node. Have it point where the 3 is pointing. Change the 3 to point to the 7. So that's order 1 if we know where to add. But if we're going to search, if we're saying I want to add a 7 after a 3, we have to start at the beginning and move through the list. So this could be order n to find where to insert, where to add. So inserting in the middle is still tricky if we care about where we put it. And again, we're going to care if we have a sorted linked list, because sorting is going to eventually make searching very efficient. So for now, searching a sorted array is going to be log n. Searching a sorted linked list is still going to be order n, because we don't have a way to jump into the middle of our linked list. If we want to know, is there a 1 in my list, we have to start at the beginning and just follow it from node to node till we either find the 1 or we find the end of the list. We'll take care of that in a few weeks when we talk about binary search trees. But for now, the takeaway is if we want to put something in the middle, yeah, we might have to do order n to find the right spot to insert, but then the actual insertion is order 1. So later on we'll figure out how to quickly get to where we want to insert, so that if our list is sorted, we can add a new piece of data and keep our list sorted. And that's going to look something like this. We're going to have, you know, say our 2, 3, 5, 11, 13, 17, and we want to add 7. Well, we're just going to make a new node 7. We're going to find where it should go. It's got to go after 2, 3, 5. It's got to go before 11. So we'll point this to the node it's going before, and we'll take the previous node and point to our new one. So once we know where to put it, it's a fixed operation, order 1. Alright, so that's why we're working with a linked list, because it's going to make some things more efficient, but then it's going to let us move to binary search trees, which are going to be significantly more efficient. Alright, so that's the first goal of this lecture, was the motivation. The second goal is going to be talking about abstract data types. Alright, let's talk about abstract data types. So, you know, we've got this idea of a linked list. We're going to have these nodes that are connected to each other, and so on. And we're going to want to do things with this, and we can write code. You know, we can just do like we did in the previous video, write some code to, you know, move from one node to the other and so on. But to make this a useful data structure, we want to create a set of functions that are going to interact with this. Something we can think of as an interface to our linked list. A linked list is a type of data structure. So we want an interface to our data structure. Interface is just a set of functions that will let us manipulate this by making function calls. So for example, we might want to initialize our list. We might want to add something to our list, search for something in our list, print our list, and maybe delete something from our list. And so we could define our interface to say, you know, when we say init, we're going to get back some kind of handle that we can use for accessing our list. And so we might have, you know, a struct node and have a pointer called handle that init returns. And when we call init, we get back this thing, this pointer that we can use to say, okay, here's my list. And then if we want to add something to the list, we might give it our handle and an integer that we want to add. And if we want to search for something, we might give it the handle to the list, the integer we're searching for, and it might return an int, saying, for example, 1 equals found, 0 equals not found. And if we want to print our list, we could just give it that thing that points to the first node. And if we want to delete something from the list, we could give it a handle and the thing we want to delete. Alright, so here's the idea. We can write the code for these things, and we're going to develop some of that code right now, and you're going to work on some of it in your problem set. We can write the code for these functions, and then we can say, hey, here's a set of functions for interacting with a linked list. This is your interface to the linked list. And all anybody needs to know is how to use these functions. If they want to start an empty linked list, they'll call init. If they want to add a number to it, like 5, they'll say add parentheses the name of the list, comma 5. And if they want to search for something, they'll say search the name of the list and the number they're searching for, and they'll look at the return value. If it's a 1, that thing is found, otherwise it's not. Alright, what's important here is that, we're going to develop these functions that are going to do things like move from one node in the list to the next, and if we need to insert something in the list, we're going to make a new node and change these pointers and so on. But the person using this is not going to know that. They're not going to know anything about how we make our list do what it does. So there's going to be the user's notion of a list, and then there's going to be some interface that we provide, and then there's going to be the low-level details. And these are going to be hidden from the user. They're not going to know anything about this, they're not going to care about this, they're not going to need to know what the low-level details are, how our list does what it does. All they're going to have is this interface, and they're going to know, hey, if I say delete from this list the number 7, hey, this number 7 should go away, my 5 should point to the 11. So this is the idea of what we call an ADT. This is an abstract data type. And an abstract data type means we're thinking about the things that this data structure does without thinking about how those things happen. So a linked list is a collection of data with pointers where each pointer points to the next thing in the list. It's this structure, right? That's an abstract list. And with an abstract list, we can add to it, we can search it, we can print it, we can delete from it, we can initialize it, right? That's our view of an abstract linked list. Now, a particular linked list is going to mean, in addition to this, the actual C statements that cause these things to do what they're supposed to do. That's a implementation of a linked list, sometimes called an instantiation of a linked list. But as an abstract notion, a linked list is just this collection of data pointing from one to the next, and this interface, this set of functions that we can use for interacting with it. And here's how we know that this makes an abstract data type, because we're going to look at some C code for doing these low-level details. But you could also write these functions so that they send a text message to somebody, and that person, when they get a text message which says add 5 to this list, they could just go ahead and put a 5 in there and change the arrows. And when they get a text message saying, hey, tell me if the number 7 is in the list, they could look at their piece of paper and say, oh yeah, 7, and they'll send back a text message that says 1, and the search function will return that. And these low-level details could be, a series of messages being sent to a human with a chalkboard or a piece of paper who's keeping track of what's in the list and responding to inquiries or commands on how to work that list. And whether we're writing low-level C code or we're sending messages to somebody on a desert island with a cell phone, or we're invoking some kind of magic and talking to a genie, right? The user does not care. The user is just going to use these functions to manipulate the list, and whatever's going on down here doesn't make any difference to them. All of these things, we could do these things with an array. We can take an array and we can insert things in the middle, we can search for the array, we can delete things from the array. And if we decided we were going to write these functions using arrays instead of linked lists, the code up here would not have to change, right? The person who's making these function calls, they don't care how those functions are working. They just care what they do. So this is an idea that we're going to come back to again and again throughout this course and 223 in spring. The idea of an abstract data type versus a particular implementation of a data type. So we're going to be doing both. We're going to be working with abstract lists and we're going to be working with implementing them. What we want to work on next right now is thinking about what we have to do to make some of these functions actually do what they're supposed to do. Alright, so there's a lot of ways we can do this. Let's start writing some code and take some of these functions and bundle them together so that they work collectively to create a linked list for us. So here's what we're going to do. Let's start with the code we had yesterday. And you know, that defined a node structure and we used malloc and size of and all of this kind of stuff. We don't want to do that, right? We just want a linked list. So I'm going to do the following. I'm going to make something called a mylist, which is a pointer to a struct node. And I'm going to say, let's initialize this list. So mylist equals init. So create a new linked list. And then I'm going to say add mylist, comma, let's add the number 10. And then let's add the number 20 and the number 30. And then let's print my list. Alright, so this is going to be our whole main program. We're going to create an empty linked list. We're going to start adding things to it. And then we're going to print out the contents of that list. Alright, now here's a little trick we're going to use. Remember, we're starting off with an empty list. And when we want to add this first number 10 to it, our result should be a list that looks like this. And we're going to use this business of having the next field be null so that we know, hey, there actually is not a new node after this. It's just a 10. Alright, so if we call our init function up here, what should that init function return? We're saying it's going to return a pointer to a mylist, but you know, when we initialize a list, the list is empty. Our empty list looks like this. It's just, there's nothing there, right? But nothing is a really hard thing to work with. The problem is, if we simply returned, you know, something like null, and then we try to add 10 to a null list, that's tricky, right? And this handle to our list can't be null, right? It's like a coffee cup with a missing handle. You can't pick it up, right? But if you don't have a coffee cup, how can you have a handle on the coffee cup to begin, you know, building your list? So we're going to do something a little slick here. We're going to use what's called a Sentinel node. And the idea of a Sentinel node is it's going to be a placeholder. It's going to be a node that exists, but we don't really use the value of. So our empty list is going to look like this. So this is an empty list. When we add the number 10 to our empty list, our list is going to look like this. There's going to be our Sentinel node. Here's going to be our new node, a 10 with a null, and our Sentinel is going to point to that. So this is a list with one node. And this is confusing, right? I've said this is an empty list, but there's a node there. I've said this is a list with one node, but it looks like there's two nodes there. So what's going on? This Sentinel node is not considered part of the list. It's there, it always exists, it is the handle to the list. But that node itself is not considered part of the list. In other words, this data field up here does not contain the first number in the list. So we don't really care what's in this data field up at the top. And we might put a special value in there so we recognize it, but we really don't care what's in there. The only thing the Sentinel node does is it points to the first node of the list. So if we have a list with two nodes, it's going to look like this. There's going to be a Sentinel. That's going to point to our first node. That's going to point to our second node. And this is going to be null. The advantage of this is, number one, if we were to delete all the data from the list, we go back to this. The handle is still there. The handle still exists. That's the Sentinel node. Number two, if we want to insert in the beginning of the list, we're not changing the handle. If we wanted to insert something at what we consider the beginning of the list, that would be right here. We would change the Sentinel to point to that new node. But the Sentinel doesn't change. Once we construct a list with this init function, we have this handle that points to a Sentinel node, never changes for the duration of the existence of that list. We can delete all the data, we can insert data, we can change data, the Sentinel is always the same. So with that simplification, let's do this. Let me put another comment here. This is a pointer to the Sentinel node of the list. All right, everything else is going to stay the same. So let's write some functions for this. So let's write the init function. Let's return a pointer to the Sentinel of a new empty list. So this is going to take no arguments. It's going to return a pointer to a struct node. And what do we need to do? Well, let's make a temporary variable called temp. And let's allocate some space for it. And let's set the next field to be null. Because remember, for this to be a Sentinel, it's got to be pointing to null, so we know, hey, there's no data nodes in our list. And let's give the data field a particular value just for fun. If at some point, we're building a list with the numbers 10, 20, 30, and we try to print it out, and we see the number 99999 pop up, that will tell us, hey, we did something wrong. We're looking at the data field in this Sentinel node, and we're not supposed to, right? We're supposed to be ignoring that. So we'll give it a value that we'll recognize as saying, hey, something is wrong here. All right, so I'm going to return temp. And there we go. There's our initialization function. Now let's think about what's going on in here. I'm returning temp, so I'm making a mylist, which is the handle to a linked list. Suppose I called init again, and I said, my second list equals init. Would my second list be the same thing as my list? No. Because when I call init again, right, here's a temporary variable, malloc going to find a new memory location, store that in temp, set up the fields next in data, and then return that new memory location, and my second list would be pointing somewhere else in memory. So even though our code repeatedly uses temp, it's going to have a different value. It's going to refer to a different node in the future. So we're going to be able to have multiple linked lists and keep everything straight. Alright, so that's our init function. Let's go ahead and write an add function and a print function and then see if this is actually making sense. So, abstract data type, notion of the add function, we should just take handle to the list in an integer and append that. So let's insert at the beginning of the list. So when we want to add a new node, we're going to create a new node using malloc. We're going to point to what was the first node of the list, and then we're going to have our Sentinel point to that new node. All right, so you're going to do this again in the practice problems, but let's just put this together. So let's insert a new node at the beginning of the list. So I'll make this function void. I'll call it add. And let's call our argument Sentinel. Right, we can call it anything we want, but that's what it is. It's going to be the Sentinel node. Or we could call it handle. I keep using the word handle. Let's call it handle to the list and integer data. So first thing we have to do is make a new node. So struct node temp, I can just copy some of this. So struct node temp equals malloc size of struct node, so I've got space for it now. Temp data should be whatever this argument is that we passed in, saying, hey, I want to add, the number 17. Let's set the data field equal to 17. All right, so this is the number to store in the list. Now we need to add this node to the start of the list. Alright, so how do we add our new node to the start? We need to do two things. We need to set this thing's next field, the new node's next field, to point to what's currently the beginning of the list. Well, that's not too bad. That's just temp arrow next equals, and we should point to whatever the Sentinel node, the handle, is currently pointing to. So we're just going to say temp next equals handle next. So that's pointing to whatever was the first node of the list before we called this add function. And then, last thing we need to do is have the Sentinel node point to our new node, so it says, hey, where's the first node of the list? Oh, it's that new node that was just created. So now we're going to say handle next equals temp. And so let me add a comment here. Sentinel now points to this new first node. Alright, and there's our add function. So again, we're putting in a handle to the list and a piece of data we want to add to the list. We're going to take a struct node pointer, find somewhere to point it to, set the data field to whatever data we're storing in the list, have this new node point where the Sentinel node is pointing, and then have the Sentinel node point to the new node. So we're sandwiching this new node in between the Sentinel and whatever was the next node in the list. So if we have a Sentinel and we have a list containing 20, and we're putting in a new node 10, we'll have the new node point to the first node and have the Sentinel point to our new node. So now this is inserted in the beginning of the list. And for our edge case, if we had an empty list, which looks like this, when we add our first node, let's say we go ahead and we add a 10, we're going to create a new node. We're going to say this should point where the Sentinel is pointing. Well, the Sentinel is pointing to null, so this will point to null. And then we're going to change the Sentinel to point to this. That's what happens when we add to an empty list, and that's exactly what we want. We want the Sentinel pointing to the first node. So there is no edge case for adding if we have a Sentinel node. This code should work in all cases. Alright, last thing we want to do is print the list. So we'll do a void function called print, takes a handle, and should print it out. Alright, so how are we going to do this? So I'm going to draw a picture of a list. So here's a Sentinel. And let's say this points to a 10. And that points to a 20. And that points to a 30, and this is null. So here's our handle, which is, a Sentinel. Alright, so the first thing I want to print is 10. All I've got, the only argument I'm passing to my print function is a pointer to this handle. So when I start my function, I can set temp equal to this handle. But I don't want to print this data field up here. That's my magic number 99999. I don't want to print that. I want to start by printing this node. So I'm actually going to begin by having temp point to our first data node, not the Sentinel node. So I'm going to begin by saying temp equals handle next. So that's the first data node. Or if our list is empty, that could be null. Because, for an empty list like this, if I say temp equals handle arrow next, temp is going to be null. But in this case, temp is going to point to this node. So what am I going to do? I'm going to print temp arrow data. That'll print out the 10, and then I want to move to the next node, so I'm going to say temp equals temp arrow next. So now temp will point here. I'll print out the 20. I'll set temp equal to temp arrow next. I'll print out the data as 30. I'll set temp equal to temp arrow next. Well, temp arrow next is null, so temp will now be equal to null. Now if I try to print temp arrow data, I'm going to try to follow my null pointer. I'm going to segfault. But I just printed out the 30. That's the last node in the list. I am done. So I'm going to do this loop, and I'm going to loop while temp is not null. And when I change temp and it turns out to be null, that's exactly the point where I want to stop looping through my list. So these termination conditions and the initialization conditions, these are one of the tricky spots in dealing with structures like this, linked lists. And it's easy to be off by one. It's easy to start too early in the list or to start with the second node instead of the first. It's easy to stop printing your list one spot too soon, or to try and stop one spot too late and end up segfaulting. So the pictures will help, right? Draw a picture, think about your code in sort of pseudocode, kind of higher level, and pretend you're a computer. Go through and see what your code is going to do, see what you want it to do. Where do you want it to begin, where do you want it to stop? I want it to begin at handle arrow next. I want it to stop after I've changed temp, and temp is now null. So let's just code this up and wrap up this, this video by seeing what this does. So I'm going to start with the first node, and I'm going to say while temp is not equal to null, let's print out temp arrow data. And I'm going to print this out with a new line at the end. It's going to print one line per number. But remember, when you do print statements, if you don't put a new line at the end, it doesn't actually print. And if I get an error somewhere, I want to see as much progress as has actually happened. And if I don't print a new line till I'm done with this print function and something goes wrong in the middle, I'll have no way of knowing if it printed anything and it was buffered or if it died before it printed. So when you're debugging code, when you're developing code, I recommend always put new lines at the end of every print statement. And if there's debugs saying, you know, what the value of a variable is, make your debug statements clear. Print out something like, you know, the variable x is, and print out the value. Don't just start printing a bunch of numbers. All right, so let's print out the value of the data, and then let's say temp equals temp next. And this is what we call just moving down the list. So we're moving temp to the next node, and then we're going to go back to the top again. So once temp is null, we just printed the data for the last node in the list. And so we can return. So that's our print function. And let's get rid of all of this stuff. All right, if I try to compile this, I'm going to get a lot of backtalk from the compiler. Right, look at all those error messages. But don't panic, right? Look at the first one, and it says implicit declaration of function init. When you see something like this, implicit declaration, it means that instead of explicitly telling the system what init is, I'm letting it figure it out for itself. It's implicitly declared by how it's being used. Okay, this is what function prototyping is about. Function prototyping says, don't try to figure out what a function is. When I call init, don't try to figure out, you know, that it takes no arguments and it returns a struct node star. Let me tell you explicitly what init is. So I'm going to add some function prototypes. And remember, I'm going to put them after the struct statement. And I'm going to put a little comment next to each one saying, hey, this is what each function does. So my add function, and so I'm using a shift Y to copy this to the yank buffer and then a lowercase p to paste it. This adds a node to the start of the list. And here I'm using a % to find the matching curly bracket. And then a K to go up 1, a Shift Y to yank, a 1 Shift G to go to the top, and then I'm just hitting return to come down here and hitting a lowercase p to put, $sign to get to the end, and a semicolon to add a semicolon, and then I can write a comment. And I'll say we're printing one number per line. There's a DD to clean that up. All right, so this is our interface to the linked list. This is our collection of functions with which the user will interact with the linked list. And since we're adding to the beginning, let me just change around the order of these. Let's add a 30 first, and then a 20, and then a 10, so that our list comes out, you know, 10, 20, 30, sorted. All right, so let's see how we did. Let's go ahead and compile this. And we got rid of all our errors. They were all just implicit declarations. Let's go ahead and run it. And there's our list, 10, 20, 30. All right, that was a lot of work. But most of that work, all of this stuff, this is invisible to the user, right? All this stuff from here on down, we could throw all this inside some kind of function library. And the main program, the thing that the user is dealing with, would just be this. Hey, there's my declaration of my list. Here's where I initialize it. Here's where I add some stuff. Here's where I print it. All right, and then just to see that this is sort of magic, let's make a my second list. Let's call my second list equals init. And let's add some things to our second list. So we'll store some prime numbers in our second list. All right, we're not changing any of the details of, you know, Sentinel nodes and changing pointers and following pointers and all of that stuff. That's all hidden from us now, right? We're just thinking of this as, you know, a package with an interface for dealing with linked lists. So I declare my list in my second list. I call initialize to initialize each of them. I call add on my list. I call add on my second list. And I have two completely independent lists at this point. There's my list, there's my second list. And if I run this, right, there's the values for my list. There's the values for my second list. So I could do something like this. Let's print out what my list looks like. And then let's print out my second list. Just to make this a little clearer, and I'm throwing some extra spaces in here. So there's my list, there's my second list. And these really are independent lists, right? I can interleave these add statements. Right, I can add to my second list, my second list, my list. I can mix these up and so on, and it doesn't change anything because I've got two completely separate data structures called linked lists with two separate handles to them. And when I want to add to one, I just say add in the name of that list. When I want to add to the other, I just say add the name of that list. Right? So this is the start of like a nice linked list package, right? We could not have to worry about all of this stuff, right? The business with malloc and size of and pointers and nulls and magic numbers and all that kind of stuff. That's all invisible. And eventually what we'll do is we'll take all of this stuff and we'll throw it into a separate file, and we'll take the declaration of a struct node and throw that into a separate file. And we'll use some type defs maybe to make things even more transparent to the user or hidden from the user. And then we'll just have, you know, this notion of, oh, I want a linked list. Okay, I'll just declare something like this. I'll call init, and then I'll start adding things, and I'll print. And we can write a search function, we can write a delete function, and so on and so forth. All right, so that's the basic setup. All right, so we'll work with this in the practice problems. You'll basically be recreating this code on your own, but you really want to do this from scratch. Don't copy down this code from the video and then just type it in. You want to develop it yourself, and the whole key to being able to do this, again, is going back to pictures. You want to draw pictures, you want to think about what you want to do, and then get the practice of writing C code that does what it is that you're after. And you've got to develop that connection between intent and instruction. And once you're able to do that, then you can do anything you want in your program, right? You just decide how you want memory to be manipulated, and you write the statements to make it happen. And debugging is just a matter of finding out where there was some disconnect between intent and instruction. So the practice problems will work on this, and we'll take you through basically this set of functions, and then in the following lecture, part 3 of linked lists, we'll start taking more functions. We'll figure out how to delete, how to insert to keep a list sorted, and we'll start using GDB to actually go inside the memory of the computer and see what our linked list looks like, and that'll be really, really important for debugging, to be able to see what our instructions have actually done versus what we thought they were going to do. So that'll be the future lecture, but for now we're going to basically just work with this initial version of a linked list package where we can initialize, add, and print a list. All right, have fun. Thanks.